Okay, welcome back from your break. This is the fourth video in the Reynolds transport theorem and radial hydraulic jump lecture. This is the slide where we just finished, where I described essentially what creates a circular hydraulic jump, the reduction in velocity leading to a drop in Froude number, which causes the fluid to go from supercritical to subcritical at some point, and that barrier, that boundary, is the jump. What I wanted to show you now was a video that I just made in my kitchen sink that describes probably what you guys do on a almost daily basis, perhaps without realizing it, which is the creation of hydraulic jumps every time you turn on a faucet. So let's transition to that, and then we'll come back and continue with this lecture. Okay, so back to me. So that was me doing hydraulic jump experiments in my kitchen sink, just to show you that there's nothing magical or special about them. You can produce them at home pretty much every time you turn on a faucet. So now we're ready to transition to the next presentation objective, which is to show that radial hydraulic jumps simultaneously satisfy both mass and linear momentum conservation equations that originate from the Reynolds transport theorem. So what I'm going to show you here, this is that same kind of blue shape showing the water coming down and then spreading spreading outwards that we saw a few slides back, and that's just to give you a familiar shape. I'm about to remove it from the screen and show you a similar shape with a lot of kind of variables affixed to it. But the key thing from this portion of the analysis is that circular or radial hydraulic jumps must obey both the conservation of mass and the conservation of linear momentum. And both of those equations, of course, come from the Reynolds transport theorem. And it turns out that in addition to the radius being set by the Froude number transitioning from supercritical to subcritical crossing through 1, the radius is also set by the need of the fluid to simultaneously satisfy both of those conservation laws. So to give you a series of or a set of parameters to work with, I'm going to remove this nice blue shape and leave you with something slightly more complicated, but that has all the important variables in it. So D is the diameter of the nozzle. A is the diameter of the column of fluid that comes out of the nozzle. R1 is some radius between the center column of fluid and the beginning of the hydraulic jump. R2 is a radius between that central column of fluid and some location beyond the hydraulic jump. H1 is the height of the fluid before the hydraulic jump. H2 is the height of the fluid after the hydraulic jump. Here, of course, this ragged shape is the hydraulic jump itself. And then we have V1, which is the velocity entering this dotted area, which I'll describe in a second. And then this V2 is the area leaving the velocity leaving that dotted area. The dotted area itself you probably recognize as a control volume from Reynolds transport theorem analysis, and the dotted line itself is essentially the control surface of that control volume. And so you know probably from conservation of linear momentum that you're not only concerned with momentum crossing a system boundary, but also forces imposed on the system boundary. And so these blue triangles represent the hydrostatic force as a result of pressure being imposed both on the inlet to the control volume here and to the outlet of the control volume here. So all of the variables that we need to do both mass conservation and momentum conservation are contained within this image. Okay, so I've hit my 7 minutes, so we'll take a pause here and come back for the next video. See you in a moment.